if the error, thank you, the error is greater than a tolerance value, which in this case is going to be 1 to the power of -6, that just means the difference in between the output and the input is going to be greater, has to be greater than this value. Otherwise, we have reached a steady state, meaning that we do not have much difference in between the input and the output. So at that point, we will be able to stop the execution. Or if we reach 300 iterations, then you will just be able to have that. Okay. Unfortunately, we are not going to see the simulation in like visually, but you get the idea of what is actually happening here. Now let's take a look at these two operations, the calc next and the swap. So the calc next is going to be this one here. The swap is going to be this one here. And we have some deallocation and we have an initialization function. What do you think the initialization function does? It just sets the values of the first row to 1 in A and A new. That's it. And the calc next, it is the one that does the average, right? So 0.5 or 1/4. And the addition of the j plus I plus 1, meaning the upper one, the j I minus 1, the lower one, the j minus 1 times I, meaning the left one, and the j plus 1 times a comma I, meaning the right one. So we are just doing exactly what we were doing there. Then we calculate the error, right? And we return an error, and that's it. The swap is going to do a copy from A new to A offset to the old A, and it will just take the values back. A really, really simple program, easy to understand. Anybody has any questions here? Let me see. Thank you, Stevan. Yes, that is a really good pointer. Will this work with like a different equation with constant heat input that eventually converges? Yes, I mean, this is typical what you will find in operations that have like a time, some sort of time steps, and it will have like each step you have to do some computation. So for example, if you want to consider the material, you can have a weight here that represents the different thermal dissipation constants of the different materials. Or if you want to think of a weir propagation, like a weir material that has more propagation in one direction than the other one, you can consider weights that go in these elements here. I'm not a physicist, right? Like, depends really on your area, on your field, but you will find these sort of double for loops or these sort of stencil-like operations everywhere. As Esteban pointed in there, the pattern in deep, that's a really good material you can take a look at. Can we simply disregard their existence and release that memory? Juan, can you explain to me what do you mean by their existence?
I'm sorry, there was a mention about the boundaries above.
Oh,
which is related to the previous question.
Yes.
Because he mentions about what they're trying to achieve is the steady state.
Right.
So boundaries fixed is a steady state after a very long time. So what I'm thinking of is, can you release that memory from the boundaries and just drop them off from the array?
Absolutely. It will make, you can, but it will make the offsets more complicated to calculate, because now you have to consider that every new row, you have to add 2 elements that are the edges. So before, because this is supposed to be contiguous memory space, then if you want to jump from here to here, you just say the number of elements in the row times the column that I'm trying to reach plus the number of rows elements in the row, right? Like in this case, 4, if I want to access this element here, I have to do 4 times 2 plus 3, and that's how I get here. But if I remove these elements from memory, now I can ignore them, but now I have to consider that every time that I want to go there is going to be the number of columns, like the real index in the application is going to be 1, 2, that will be 1, 2, 2, right? So this will be 2, 2. but the operation will have to consider the fact that I do not have these elements in memory. So I have to do a subtraction of 2 or a subtraction of the edge every time I want to go from the coordinates of one to the coordinates of the other. So it is possible, it's just, right, it's an optimization, and it will definitely help in some cases, but in this case, I don't think it will have a big impact.
Yeah.
Okay.
Al grupo.
Alberto, could you simply add an extra empty set of rows and columns? Couldn't you simply add an extra empty set of rows and columns? Do you mean extra empty row at the bottom, or do you mean for the edge? Alberto. Yeah, okay, excellent. Yeah, I mean, definitely there are many ways that you can represent this. And the objective is for us to be able to understand OpenMP, but it really, ultimately in the application, it will really make sense to try to optimize those elements. It will make a difference. Sometimes it will not, but again, Amdahl's law, do not waste your time on something that will not provide you with great benefits. Okay, let's continue. So we compile fast, output Laplace, give me information about profiling, add profiling in this case, include this folder so I can use the particular include tool, then Jacobi.c, Laplace.c are the 2 files that we just discussed, echo compilation successful, which is here, and then submit Laplace, which is the execution which happens here. Look, that we are only executing 300 iterations, right? If we make it larger, then we're gonna have issues when you all try to compile the same program at the same time. So what we do is we reduce the iterations at the beginning, and I did discuss this before. Originally, this value was 1,000, but if I run it for 1,000, it's going to take like 50 seconds, right? You're gonna be owning the system for 50 seconds. That means other people will not be able to access the system for 15 seconds. But as we optimize this value, the execution time is going to go below the second. And in that case, we can start increasing this iteration max value here, right? As I said earlier, you do not always want to work with the biggest problem. You want to scale down your problem really little, so you can do the profiling in a reasonable amount of time. And then after you do the profiling, after you do the optimization and the parallelization, your execution time is supposed to go down. Then you can increase the size of your program. That in order saying that differently, there is a law called Gustafsson law that says that the moment that you reduce the execution time, you just increase the size of the program, and you do more with the same execution time. That's more or less what you are doing there. Code description, already went over this. Very hot, room temperature, so that's fine. Code breakdown, the elements, the average, the calc next function, the swap function, all of that is there. Profiling the code. Here is where I suggest you stay in the terminal, but we will go over this a little bit, okay? So the nsys command is the new command for NVIDIA Insight. It used to be nvprof before. In nvprof, all you have to do is say, nvprof, this is my program, and that's it. In here, you have to say, nsys, I'm going to profile, right? I'm going to have some annotations in VTX. Please bring me the stats. Force override, so you are allowed to override the output file. Then this is going to be my output name, Laplace.q QR something, QR, I forgot the QDREP. And this is going to be my executable. So for me, this is just way too complicated to remember. So to this day, I still use nsys, nvprof, and the name of the executable, and that works as well. It's different, but it works for me. Okay, so let's see. Let's take a look at this here. Since we are going to be profiling, that means that we are going to be executing the code in the compute node. We need the submit. So this is one way of doing it. right? The other way when this runs is NSYS, and let's see if it works here, but we'll see. nvprof just means use the legacy nvprof command line. While that runs, look that this is not able to run because I'm waiting on this one as well, right? So that's going to be also the case for you. Here, what do we see? We see the while range, we see the calc range, we see the swap range, and we see the init range that come from the fact that we have an annotated code, right? We have an output file here, and we have the different contributions of execution time in between one and the other. Do remember that the while computation includes the calc, the swap, the calc and the swap, right? So this 49%, you have to understand that it also has some contributions in this 33 and this 16, right? They almost add to 49%. The rest of the time, it's being spent on other computation. Right now it's not showing us, but it is being spent in other computation. Now with nvprof, we have a similar story, right? It's just so much easier for me to remember this than the other one. Anyway, now we already downloaded the file, right? So I'm gonna just show it again. It's this one here. We already went over this timeline. Let me just make the thing is a little bit bigger. There you go. And we already went over how each of these elements represent the different computation time. If you take a look at this, it almost makes sense that this is here, that this is 32 comparison to 17. It's almost that distribution here that you see in terms of the calc versus the swap, okay? And if we zoom out, we will see that this is the execution time of the program. This is some initialization here. So for example, here is what we have as an init somewhere here. It's so small that you don't even see it. Oh, here, init, right? And it does not represent most of the computation, so do not waste your time trying to optimize the init. You will have to modify it eventually, but for other reasons, not for performance reasons. Okay. Questions. Yep, you're right. You are right, Alberto. That may be neglectable for the application. Okay.
Question, sorry.
Yeah.
Can you hear me? Right.
Yeah, I can hear you.
What happens if we don't put any flag? Is there like a way to make Insight or this toolset profile the whole code without setting any flags? For example, if we don't want to like go there and just let it profile everything, because I remember using Intel's profiler and it did the profiling for everything. It's a little bit more complex to review, but useful in certain cases.
Absolutely. Let me show you what happens if I think that I have that in the next one. Let me see. There is one here that when you profile it, it doesn't have the ranges, but I think it may be in the other one. Here, there you go. So in this case, this version here is a solution version for another exercise, right? So in this version, I do not have any annotation whatsoever. And what we see, oh man, I do have the annotations. Okay, it's not the great example, but if you do not have the annotations, what you tend to see is the name of the functions. It usually chunks the elements into functions. The difference is that sometimes some of the functions may be inlined, and if you inline a function, then you lose the information of the function because all the code gets put together, right? So sometimes you will not see the functions that you are expecting to see, or you will see weird names, and that is just because of the optimization. So it is good to annotate the code, but I usually never do it unless I start having issues or I really need to specify which segment of code I want to provide. There are ways that you can also, for example, turn on and off the profiler if you have a large overhead, for example, loading files from disk, right? And you don't want to consider that. There are also functions that will allow you to turn on and off the profiler. The problem is, if you instrument your code, that means if you add elements to your code, you are making your code specific to that particular profiler. If you're going to be using VTune, you will have to use the VTune tools. If you're gonna be using NVIDIA's tools, then you're gonna have to use the NVIDIA annotation tools. And if you go down, for example, into CUPT, which is a CUDA profiling tools interface, you still are able to see the different CUDA profile elements, like the different CUDA codes, and you have more control to obtain information really specific to the code. The difference here in between one way and the other one is that this profiling here is based on the sampling here, right? Each of these ticks, as we saw earlier, each of these ticks represent a different sampling point. The profiler, what it's doing is saying, what are you doing right now, code? What are you doing right now, code? What is your program counter? What are you executing? And it's obtaining that information, and based on that information, it creates the timeline. The other type of profiling, we specify the sampling points through the use of functions. And so it's a little bit different to this. There are pros and cons, right? And there are profilers that are purely based on sampling, and there are profilers that are purely based on you adding elements to your code, like PAPI or things like that. Is that useful?
Yeah, thank you.
Mm-hmm. Okay. I think that we can continue to the next one. Yeah. I will just show you that whenever we have GPU code here, we're going to start seeing other things. So this particular case is a GPU execution. You probably got excited right away by looking at this number, right? Let's remember what our base case was. 14 seconds. Let's take a look at what our GPU case is. Not that one. Not that one. This guy, 0.7 seconds, right? So that's a really good speed up. And we also have another number here, which is 3.8 seconds. We'll have to later on take a look at if this is the if it is executing a smaller problem, or if it is the CPU version. But it's not important right now because we're gonna go over that. Any questions before I move to the next section? There's not. Okay. Module 3. I'm gonna close this. Okay, now finally we get into OpenACC. Excellent. Okay, OpenACC directives, of course, because they are directives, we're gonna have to take a look at the syntax of those directives. I will stop in a second and also show the Fortran syntax, but I will begin with the C++ syntax. We're gonna take a look at the parallel directive, the kernels directive, the loop directive, and the different elements that compose those directives. And those are the ones that we're gonna begin with, okay? So the syntax is, in C, is going to be a hashtag or pound or whatever you want to call this symbol here. So pound pragma, ACC, to specify that this pragma is ACC. Pound pragma by itself is a compiler element. It is an annotation to the compiler that can be ACC, or meaning OpenACC, OpenMP, or even intrinsic pragmas that the compiler comes out of the box. So one pragma right now that we are using is ACC, meaning this is going to be compiled using the ACC directive support. The name of the directive and the different clauses, right? So we did see something like this in OpenMP, that we had a directive and we had the concept of a clause, which was a way to modify the information that we were applying to the directive. In Fortran, what we are going to have is a comment starting with the exclamation mark, followed by a $, followed by the word ACC, and then after that is going to be exactly the same, directive and clauses. Right? There are differences in between C, C++, and Fortran, but they are mostly based on the differences in the base language. So for example, in Fortran out of the box supports array ranges, right? And it supports array ranges. I believe the syntax is something like beginning and end. But in the C++, whenever we see array ranges here, in C++, there is no native support for array ranges, but OpenMP and OpenACC support array ranges, but the syntax is a little bit different to Fortran. So what they did was use the Fortran syntax for Fortran array ranges and use the C and C++ syntax for C and C++ array ranges. But those changes are like minimal between one and the other. Okay. Oh, there you go. Give you 1 second to read that. Okay, let's begin with the parallel. And finally, we are starting to parallelize our code. So the first thing that we need to understand about the parallel directive is that it creates something that we're going to refer to gangs. The gangs are going to be the highest level of parallel, the highest parallel level that we're going to have in OpenACC. And it represents like independent workers, people that are, let's say, people that are hard to synchronize, right? People that are big in size and that will have a lot of people below them, right? So meaning if you are familiar with the NVIDIA architectures, the gangs will somehow map to the concept of a streaming multiprocessor, or SM. That is kind of like the different cores that the NVIDIA GPU has in the system. The gangs are completely independent from each other, right? And from other groups of threads. They tend to group together different threads. So inside of a gang, we're gonna have multiple threads. And if you have a parallel directive, whatever code you have inside of that, meaning whatever code is enclosed by the beginning bracket and the end bracket, is going to be executed by the different gangs redundantly, meaning that whatever code you have inside, and I'm going to give an example here, is going to be exactly the same for each of the gangs that you have in the system, right? So the parallel directive produces a redundant execution of code because all of them are going to be doing exactly the same. This is similar to OpenMP when you say parallel, and all of them all of the threads end up executing the same code. This is different to OpenACC, to OpenMP, in the sense that you do not have so much control over the number of threads, the thread limit, and you do not have a concept of give me the ID of my, it's not as, it tries to abstract away that information from the programmer. So just to give an example, if we were to parallelize a for loop, like in this case, and we had a parallel directive bit outside of it, every single gang that we create is going to execute the loop from the iteration 0 to the iteration n, right? Here, I am not parallelizing the loop. I am multiplying the execution of the loop by the number of gangs that I created with the parallel directive, right? If I want to distribute a loop across the different gangs, I have to use the loop directive, which we will see in a second. So in this case, every single gang executes from iteration 0 to the iteration n, meaning that every single gang is doing all the work that we are supposed to be doing, right? There is no parallelization and there is not going to be any performance gains here. So if we want to specify that we are going to have a loop and that we want that loop to be work shared across the different gangs, then we use the loop directive. The loop directive is independent from the parallel directive, right? And what we say is, this is going to be my creation of gangs. So I create the different workers. And then please take a look at this loop here, which is completely independent because I'm just assigning a value of I of 0 into the I position and distribute a chunk of each of that loop into each of the different gangs. For Fortran, look at this, it's really similar. Exclamation mark, $ACC parallel, exclamation mark, $ACC loop. And then you have the do loop that you usually have in Fortran. Then this is a really common mistake at the beginning that you say, oh, I'm going to parallelize this loop. So I just put the parallel directive and I'm supposed to be parallelizing everything. And it's not the case. You are going to parallelize the loop, you have to use the parallel and you have to use the loop. And as I said, because these are so commonly going together, then you will see them in a single line like this, or what they call it a combined directive, meaning that you are combining one directive with the other directive. So it's pragma, ACC, parallel, loop. Give me an ACC code that creates some gangs and distributes a loop into the different work sharing elements, right? So this is just the typical code that you will begin with. So what happens here is that whenever you put that loop there, you are giving a chunk, you're creating the threads within the gang and you're giving the chunk for that particular gang, you're giving a chunk of the iteration, meaning in this case, if we were to consider a static scheduling, we have 3 times 2, 6 gangs, right? So we will take n and we'll divide it by 6, and then this will take the first 6, then this will take the second 6, then this will take the third 6, right? So each gang is going to be working on an independent segment of code. And in the case of OpenACC, when you use loop, it also creates the threads, right? Okay, so commonly way of parallelizing code. Now, more often than not, your code is not just going to have a single loop. So what do? You have pragma ACC parallel loop into the first loop, then you have pragma ACC parallel loop into the second loop. Any questions? Wait, you ignore the adjacent example. Oh, the difference in between using parallel loop and together and separate? Is that what you mean, Alberto?
Yeah, but I think you can actually, I think you can't use loop by itself, right? It has to be within a parallel region. Am I right?
Yeah, it has to be within a parallel region, exactly.
Okay,
it's the way that we say we're going to start parallelism. The reason why they put them together is because this is much nicer to look at than this. So it just becomes a cleaner code. That's why they add combined directives. Is just a way of reducing the size of the code and the complexity of the code. And usually when you have combined directives, there are clauses that apply to parallel and there are clauses that apply to loop. So you will just use them here in any order after that. Okay, so loop directive. So we take a single loop, we parallelize it, so we can provide additional information about how that loop behaves. For example, it is independent, it is a sequential loop, or elements like that. And you kind of like describe a segment of work that OpenACC will take and the compiler will take and will distribute it into the different gangs and into different threads that we create, okay? So in this case, for example, if you have a parallel region and you have a loop that is a pragma ACC loop that is here, question for you guys is, how many times is this line here executed? The A of I equal to 0. Almost, yeah. It will be n times gangs, right? Not so much n times threads, right? Because the parallel loop, what we are doing is creating gangs, right? And then the threads, we are creating them in the loop. So exactly, look at this region here of code is executed for every single gang that we create, while this one here is the one that is distributed across the different threads. Okay. So if we wanted to do this in parallel, what we can do is we create a parallel region and we use ACC loop and ACC loop. I thought they were going to explain the loop directive. Okay, I'm gonna go over the kernel's directive because it's a little bit different, but I think that the kernel sees something that they explain in a second. So the parallel directive Yeah, no, let me just finish the parallel directive and then I will go over the kernels. Kernel directive is important, but yeah. What controls the number of created gangs? Available threads divided by cores. There is a default number that is created, but we will see that there are clauses that allows us to specify how many gangs and how many threads and how many workers, or not threads, they call them vectors. So how many vectors, how many workers, and how many gangs we are going to be creating, okay? There is a possibility of nesting loops, right? So usually we don't only have a single loop, but we have a collection of loops. So we have this loop here, we have a loop inside. We can say, create a number of gangs, create the loop. In this case, this loop will likely distribute this into the different gangs. And then we have another Pragma ACC loop, which will likely distribute it across the different workers. And then each vector will just go and execute this here. Okay, so there is the possibility of saying, I create this loop, I parallelize this loop. And inside of that, I have another loop. So instead of letting each thread to execute the whole loop, I'm going to parallelize that loop as well. And please distribute it across the different workers that I have. And that way I can have the different levels of parallelism that I usually have, okay? So it's really common to have to see this, and it's also really common to have loop inside loop, inside loop, inside loop, inside loop, or to have loop followed by something that we'll see later that is called collapse. There you go. Reductions. We did talk about data dependencies earlier, and there are moments where, for example, in a typical matrix multiplication like I have in the right, where we are updating just a single location of memory. In this case, we are only updating C of I of j for the k iteration, right? And that means that there is a data dependency here because I have to read the current value of C and add the value of the multiplication in between A and B in the positions ik and kj, right? So this is really common. A reduction is usually an operation that you are accumulating or that you are doing over a single location where you just say, put every iteration, please put the result into that particular location. But usually reductions require you to have operations that are commutative, right? Because you need to have something that you can swap the order in the operations, okay? I'll discuss this in a second again. But in this case, if we try to parallelize I and j, because we are gonna have multiple elements trying to subscribe to write the value of C of ij, then we will have a problem parallelizing this code because this works like a dependency in the different iterations. So what we do is we use a reduction operation. That means that we have a specific directive that allows us to say, hey, I want to take this value that is going to be written by and read by all the different threads and workers, and I want to reduce that value into a single memory location. So in this case, k of 0, k of 1, k of 2, k of 3 are all going into C of ij, right? So the solution is, we say, if we were to parallelize this, of course, we are going to have a problem because all of them are going to be hitting the same location and they are going to be stepping on each other's foot. So the reduction class, what it does is we create a memory location where we are going to do that operation, and the compiler is in charge of doing that synchronization on the temp variable whenever that happens. So it will create the necessary synchronization operations to make sure that you read and write into that location, and that at the end of the loop of the parallelization, the operations happen in any order, but they happen consistently with what you wanted to have at the beginning. Okay, so in this case, we say pragma parallel ACC loop, and we say that there is going to be a reduction on the temp location. And then after we finish the for loop, we execute the Cij equal to temp, because now we know that this is not going to be parallelized. Yeah. So one thing to understand is that sometimes compilers are able to catch on values that may be reducted, right? That may be something like this, that you are storing and reading from the variable temp here. So sometimes even if you don't put the reduction, the compiler will be able to say, hey, I found a reduction and I'm going to add it there. But my recommendation is do not rely on the compiler in this case. It's better to have it explicit, especially because it allows you to have more information about that segment of code. Okay. And as I said earlier, reduction operations have to be commutative because you now are going to be executing them in any order. So you have to rely on operations that you can do. For example, why can I not reduce with a subtraction? Because the A minus B is different to B minus A. It's two different operations, right? I can reduce an addition with a multiplication of -1 inside of the core, inside of the loop, but different story. Okay, the operations that are currently supported by OpenACC are addition, multiplication, give me the maximum value, give me a minimum value, bitwise and bitwise or, logical and logical or. If we are reducing on the inner loop, do all threads gang have to wait for each other to finish working on that position? There are ways to implement reductions differently. One way, the naive way, is to have a scheme like that, where every time you're going to touch that memory position, you put locks around the memory position to be able to acquire it, modify it, read it, modify it, and then release it. But more often than not, what compilers do is they use private values, which means locations of memory that only can be seen by the particular thread or by the particular group of threads, that will obtain the value or the reduction within that particular value. And then there is going to be a reduction operations that happen at the end of the execution of the workers or the vectors or the gangs. And that becomes like a tree where you have all the results here at the top. Then you reduce some of those results into a low next level, then you do another reduction. So it becomes like a tree reduction. And that tends to be more optimal than just doing the blocking version as you described. Does that make sense?
Hi, Professor. Well, my question was, like, it does make sense, but my question was related to what happens if we have like four gangs or threads, and they are updating that position, and what happens if one of the threads takes a lot more for any reason, and the other threads are already like available for going for the next position? Do they go for the next position and the other thread stays alone doing its work, or do they all have to wait until the values are calculated to do the reduction and they go for the next position?
Usually, at the gang level, there is no synchronization. They wait for the final result, but there is no synchronization. At the vector level, all the threads are usually going to be taking the same, because more often than not, the hardware that executes them are closely tied, so they have to execute at the same time. That is the concept of warp in CUDA. And at the worker level, there is the possibility of having synchronization. But if you have work sharing, meaning that if you are distributing a big chunk of data or a big chunk of iterations, they do not have to wait on each other to do the optimization. They can start working on the next chunk. So it depends, as I said, depends on the implementation of the compiler, but more often than not, you do not have that synchronization there until you finish all the different work, right? Think about this. You think that everything is being executed in parallel in the worker level, but in reality, what is happening is that there is some sort of a scheduler that is determining what is executed in parallel and what is waiting for the next iteration. So that you cannot really have a thread being blocked to wait for the results on the other threads, because there is no a real overlapping of all the different threads. So you do not have the possibility of saying, I'm going to block this thread, so I wait for the other thread. Let me try to explain this better. If you have a core and your code says, I'm going to be waiting for another thread, but the way that you are waiting for that is just making the core spin on itself until something happens, you may end up with a deadlock because the other thread may not have enough resources for it to be able to be evaluated. So they avoid that completely. by not allowing something that is blocking to happen inside a thread and having some sort of preemption, meaning the possibility of swapping core threads until the other one can happen. It's a really convoluted answer, but it really depends on many factors. So does that make sense, or is that more clear? Or
Yeah, Professor, thank you.
okay. So things that you cannot do, you cannot reduce on an array element, and you cannot reduce on data members. So you cannot do a struct or I forgot the name on Fortran. So what you want to do is you want to have something like a temporary value where you do the reduction and then you do the assignment at the end of the, so you have to do that double step yourself, okay? So these two are forbidden. Now, that's why I didn't want to go into a kernels directive earlier, because there is a section for kernels. When we do parallel and loops, what we are saying is, I'm telling the compiler, I know what I'm doing, and I'm taking control over the parallelization of the code. There is a second way of doing this, is through the use of kernels. That is a way of saying, compiler, do your best to give me some parallelization, right? So different to parallel, when you use kernels, you will be creating gangs, but it's not a redundant execution. It's a way of saying, hey, take a look at the code that is within this region and figure out how you can parallelize it the best, right? So it will almost do everything for you. So in this case, if I just say pragma ACC kernels and I leave something like this, then the compiler will create the gangs, but it will also realize that this is a completely independent loop, and it will do the parallelization for you to the best of its ability, right? So a lot of time what you do is you start the parallelization process, you put a kernel in there, and that tends to work. You use minfo equal to all or minfo equal to Excel to give information, to get information about what the compiler is doing. And also because the compiler is going to give you remarks like, I was not able to parallelize this loop because I saw a dependency, or because there are elements that I do not know if they are dependent or not from each other. For example, the case of the pointer that we discussed earlier. Okay. And this is usually the easiest way to approach a parallelization problem. So with the kernel, you can just say, hey, try to parallelize it and it will do its best. Same for many loops. You don't really have to do anything, because the kernel directive is going to be able to recognize the different loops and it's going to do its best to do the parallelization, right? So by just doing this kernels thing, the compiler will just produce everything you need to do for the parallelization, right? I do not, so I'm not a Fortran expert, but there are many cases in Fortran where you can do array operations, right? Like in this case, you are making all the elements be an equal value of 1, then you're making all the elements be an equal value of 2, and then you're making C equal to this addition of element-wise addition of the different elements of A and B, right? If you were to parallelize this without the kernels, without the directive, with the parallel and the loop directives, you will have to break this into do loops operations, and then you're gonna have to do the parallel and the loop. But if you are using kernels, it will be able to recognize this as a loop, and it will be able to parallelize it for you. That's for you, Luis, who knows this better than I do. Right, like I cannot do a parallel loop on an operation like this. Okay. So in kernels, the compiler completely decides how to parallelize it and what to parallelize. In the parallel, we are the ones who are deciding what to parallelize and how to. And in the kernels, the compiler does its best to guarantee the correctness, but in the parallel, the programmer is the one that has to guarantee the correctness, meaning that in the kernel, in the parallel, you can make mistakes, you can enforce data races, and it's up to you to make sure that you don't do that. But in the kernel, the compiler will be really cautious on what it does, and it will try to do its best to do the parallelization. And in the kernels, you are using the different loop levels, like you just get them all at the same time. And in the parallel, you have to specify each loop as an independent loop clause, directive, sorry. Okay, so you have a range of things that you can work on. Okay, so when we start doing ACC, we have to tell the compiler, please parallelize this piece of code, okay? So the way that it does that is you first specify -ACC. This -ACC is not needed anymore as long as you have the TA. So I still use it, but it is, I think that in the recent versions, they make this flag, they made this flag optional if you have the TA. TA stands for target architecture, and it's equal to multicore, or in the case of GPU, it will be equal to Tesla, right? So in this case, we are generating a CPU parallel code for this loop, where we are just specifying that it's going to be a multicore. A big difference in between this and what OpenMP does is that here I'm not specifying the device type. I can with a device type clause, but OpenMP is a little bit more specific in, like, OpenMP has things like I just forgot the word. It will come back to me. Okay. But you can create versions of code that are specific for specific versions of devices, and that gives a little bit more of flexibility than what OpenACC does up until now, because that is always changing. Okay, so we have ACC parallel loop. I'm saying that it's going to be multi-core, and I'm asking to give me the acceleration info. What was the SIMD operations in the previous Fortran code? Okay, give me 1 second. Let me go back to answer this question. And it broke. There you go. SIMD. You mean here? Juan? What do you mean the SIMD operations? Oh, was that an SIMD operation in the previous? So this is Fortran syntax. Fortran is, in comparison to C, Fortran is aware of an array is like a structure of data that is supported by the compiler itself. So in Fortran, you can add arrays together. In C, you have to do the iteration, right? So in this case, you are just saying, give me all the elements of A and give me all the elements of B, and add element by element into C. So it can be seen as an SIMD operation, but it doesn't have to be, because it depends on how the compiler translates that. But it's supposed to be, when you write Fortran without a parallelization whatsoever, this is supposed to run in sequential, right? It's not pure SIMD operations. They don't necessarily have to run in parallel. They may run in parallel if you have kernels, but if you do the parallel loop, it will not work, right? So it may result into an SIMD execution when you have the kernels, because the compiler will realize this is a for loop and it will do the SIMDization. Does that make sense? Good. Okay. Here in the kernel example, what we see is that we have the program. We do, look at this, we don't have, sorry, this is the parallel example. We do not have a loop directive here. The compiler is, we ask the compiler to do a ACC multicore and to give us information about how it gets the parallelization. And it goes and says, loop on line 8, this line here is parallelizable. I recognize that as a loop that has no dependency whatsoever. So I'm going to do a parallelization of that loop. So I'm going to be generating a multi-core code with Pragma ACC loop gang on this particular level, right? So kernel is smart. That's the best way of putting it on. That's correct. It is so smart that it recognizes things like dependencies, and sometimes it will be smart enough to recognize things that may or may not be dependencies, but it will treat them as dependencies. Okay, so in this case, for example, the loop is non-parallelizable because my operation I depends on the operation I minus one. So I have an interloop dependencies. So whenever I compile it, it will say on line 8, I find a loop carry dependencies of A that prevents the parallelization, right? So the loop carried backward dependencies of A prevents vectorization, meaning that because I have A of I minus one and the distance in between my current value and the next value is one element, there is no way I can parallelize this loop. So in that case, it is advisable to use kernels with dedicated linear algebra libraries such as Agent or Armadillo. Do you mean using those libraries within the call? Like, let's say that I have a call to that library here. Yeah, so that is called interoperability. I don't think that we'll be able to get there, but there are several challenges that have to be taken into account. AHEN, for example, is a CPU library. And whenever you build the AHEN library, you generate a binary that is a CPU binary. So there are GPU versions of the different libraries that you are used to use. But if you want to use OpenACC with GPU, then you cannot just have an agent value here because you have to find the proper GPU version of that particular library. So in the CPU, you can, but you also have to be careful with one, if the library has another parallelization, right? Like it has to be trace safe, as you said, right? But if the library has another parallelization scheme, let's say that the library uses OpenMP, it will be a pain in the A to parallelize those. Because the runtime running ACC and the runtime running MP are going to probably collide to each other. OpenMP is going to say, I'm going to request threads, and this guy is going to say, I don't need threads. So I don't know the specifics about these libraries. We'll have to give it a try, but it is likely that we'll have some sort of issue if those libraries, we do not have enough information about them. On the other hand, there are ways that you can tell the compiler that functions that are outside of the compilation unit, meaning functions that you do not have access to the definition of the function, just the declaration, those functions are going to be treated as sequential, or they are going to do vectorization, or they are going to do gangs. And that way the compiler can understand that there are going to be other files that are going to be generated with OpenACC that I do not have in the same compilation unit, but it will be able to obtain the information from one file to the other. Does that make sense? There is CUDA. CUDA is for neural networks. There is a CUDA library for that. There you go. Thank you. And there is it called cuBLAS? cuBLAS, yeah. It's basic linear, yeah, cuBLAS. Typing it in the thing. So BLAS is basic linear algebra. Forgot what the S stands for. But cuBLAS is the GPU version for CUDA in there. There you go. Okay, let's go. Or is there any other questions? There you go. Thanks, Juan. Okay, I'll continue. Okay, parallel ACC loop with a non-parallel loop, right? I execute it and the code will generate a parallel version. because we are responsible to do to make sure that the code is thread safe, right? Recursions are, you can, if it is recursively creating threads, it's problematic. I think that you will have to do that if you have like a recursive functions that inside creates a kernel, like a parallel, that will not fly because there is this CPU GPU combination that it becomes complicated. But if it is a recursive function that you call within a thread, that is something that you can do. There are some in some questions there in between that I will have to try because I have never done that, but it does sound really interesting to try to do that. Recursion is usually problematic, as you know. Okay, let's go to, by the way, as I said, all I'm saying here is not my material. Do go and take a look at Michael Wolf's lectures. This guy's a genius. He's really good. One of the most important people in compilers. So there are different materials that you will be able to see, and he goes and explains many of these elements in better words than I do. Okay. Yes, you can call a kernel from another kernel, but you have to. So you create the kernel version, like you create a. I think there is a way. I have to think about it again because I don't remember if you create a function that has a different kernel and then take that function and call it from another kernel, then that tends to work. But I don't know if it will do explicitly, I don't know if it will do a dynamic parallelization. It is supposed to work, but I don't know up until what extent it does. Yes, I can. So this is the main learning OpenACC material. Oh, forgot that I have another computer. Wait, I have the chat here. I'm an idiot. And this is the main repo. This is a Docker container, so you can spawn your Docker container and do all the labs that we are doing here. And in here, you also see the slides associated to this, which is this link here. Okay, so this is where you find all the different slides. Nice. Okay, keeps increasing. Okay, so let's start module 3. We're gonna give you 20 minutes. Wow, it's 11:51 already. I really need to start to talk less. What is the program? What do you say we go for a break? Let me see. Let me take a look at the program. So 11:30. Yes, I'm way off the program time. So what they say we go for a break, and let's make it a working lunch where you work on module 3. I will be around, so you can ask me any questions. Can someone create breakout rooms so I can go around or we can go around and like ask people and things like that? And we come back at 1:30. Feel free to leave. Feel free to go get lunch, and do not worry about this. I do want to get to module 4 and 5 at least before we finish the session. Sorry, I tend to talk a lot. It's a problem I have.
No, I think it's quite okay. Thank you, Jose,
Okay.
for this nice workshop. So, so yes, as I said, I mean, we will see each other back at 1:30, right?
Mm-hmm.
So have a nice lunch and see you soon.
Yeah, and work on module 3 by yourself, so we can jump into module 4 and 5, which are more interesting.
Great.
I will be here, so if you have any questions, just don't hesitate to ask. And let me just say countdown. Thank you, everyone. I'm not going to project this in. Thank you. I'm not going to use the presentation mode because I think that's what is breaking this. So the idea here is that now that we know the abstraction is supposed to be to devices, we now have to also consider that there is going to be a more complicated architecture overall of the system, right? So we have multi-core systems where each core has its own cache, right? We know that we can work really hard on optimizing a code that works for the cache of the CPU. We usually have a high capacity memory that is usually referred to as the DRAM or just RAM, right? And we have a second device which has a lot of little cores. They have also some shared memory. They have some high bandwidth memory. The reason why we need a high bandwidth memory here is because we have many people and all of them are trying to hungrily obtain data from that memory, right? So we need a really high bandwidth memory here. That's one of the reasons why, if you take a look at the specifications of a GPU, you see that they don't use the regular DDR, double data rate DRAMs, right? But they use something called GDDR, which is the graphics double data rate, or they have HBM or really advanced memory that allows them to increase the memory bandwidth in between that particular memory and the architecture, right? Then if you were to be programming in CUDA, you will be controlling each of these segments here. Now, all of these shared memory, shared caches, and all the infrastructure for that in OpenACC becomes something that the compiler handles, and the compiler is in charge of that. And there are ways to give hints to the compiler and to optimize things for that, but that is just one way of doing it. Okay, so again, we have a host, we have a device, we have a memory host, a host memory, sorry, and we have a device memory. That means that from time to time, what we'll have to do is we will have to manually specify what region of memory I want to copy from the host to the device. That also means that there are going to be host pointers and device pointers, right? So if I say a pointer to a location of A with the address 0xFF into the host memory is going to be in a certain region. And if I go to the device and I assume that that region of memory is already allocated, then it's going to be to a different memory region. Now, technology in the memory side has improved. And now they have the possibility of having unified shared memory, meaning the possibility of looking at the device memory from the host, or the possibility of looking at the host memory from the device. Or they have what they call memory management, which allows them to simulate a unified shared memory by means of having mechanisms that will move the data around whenever you request it from one place to the other, right? So either the hardware has the infrastructure to be able to do unified shared memory, or they have a driver and a software infrastructure to be able to look at the memories as if they were unified. And we will look at this in a second as well when we discuss when we discuss memory managed memory. Sorry. Okay. So what is important here is that there will be a memory in the device, there will be a memory in the host, and there will be instructions that allow me to move data from one device to the other device, right? Okay, so CUDA managed memory. The idea here is that, as I said earlier, we look at the memory as if it were just a single memory, right? Like we allocate memory and we have that. Let's say that I got 100 floating point values, right? Like 100 floats. That region of memory is something that I can use a pointer to it and access it from the host or the device. And there will be a mechanism that will guarantee that whenever I access it from the host, it will be able to have the latest copy in the host. And whenever I access it from the device, it will be able to have the latest copy of that value into the device. But that also means that there is going to be a mechanism underneath that has to be moving data around. Like it's not like you save on every data movement. It's just that the data movements is something that you do not control yourself. And because of that, managed memory tends to have a higher cost in comparison to having no memory management, right? So in comparison to me dealing with the memory movements myself. So in the one side, I don't have to worry about memory movements. Everything is just easier to program, but it's going to be likely slower than if I have the management, if I do not have the managed memory and I do it myself. This statement has changed. I think that managed memory has become more and more smarter and smarter by the days, but it does not mean that you cannot, like there are applications where if you stay with managed memory, you will be okay, but there are applications that if you go to no managed memory, then it will be faster ultimately, right? The other thing is the managed memory is something that is specific to NVIDIA. Right now, I know 99% of the systems we get with GPUs are going to be NVIDIA, but in the next 2-3 years, we're going to start seeing AMD GPUs and we're going to start seeing Intel GPUs and who knows what, right? And so that means that it depends on their ability to provide a managed memory mechanism and their ability to make that mechanism better to be able to understand if this is going to be feasible for those architectures as well, okay? So how do we do this? We have the regular PGCC compiler line, PGCC. We say that we are going to optimize it. We say that we are going to have OpenACC, and now we say that we are going to have a target architecture that is GPU. This is just the way that, historically speaking, it's been the flag for, hey, give me a GPU. target architecture equal Tesla, right? Then we use a colon to specify that we want to have managed memory. And then we have the rest of the element. In PG Fortran, it's going to be the same. By the way, Luis, are you still there? Were you able to play around with the Fortran versions? Were you lucky with executing them and all that? Now that I see the Fortran line, I remember that I haven't been paying attention to you that much. Okay, just let me know if you are still around and if you had any issues with Fortran. Okay, so we just need to make sure that we put this on the compilation line, and that way we can just jump into managed memory. Okay. Yeah, this is what I just said. Did you? I see you are here. Were you able to execute anything? Yes, awesome, excellent. Okay, so whenever we do managed memory, we know that the piece of code that we are writing is going to use memory that has been created outside of that piece of code, right? So without managed memory, if I just create something like this, two things may happen. The first one is A is a pointer and we don't know the size, or OpenACC doesn't know the size, so it will crash, right? The second thing that happens is that we know the size, and there are some default behaviors here that will try to do the data movements into the kernels and out of the kernels, right? So if we go for managed memory, we do not have to worry about any data movement because that will happen transparently to us. But if we do not use managed memory, then we have to add more elements here that we will see in the rest of the presentation. Okay, so that means that if there is the possibility of having managed memory and I don't have to worry about it, then there is a possibility of not having managed memory and having to deal with it. And that is what we call data management. And that is what we use is we have multiple options. We're going to have some directives that allows us to do it. In a region, we are going to have directives that allows us to, in an unstructured manner, create movements back and forth or update data back and forth between the host and the device. And we are going to have clauses, not directive, but clauses in the regions that would allow us to just specify within that region what is going to be the behavior of the copies of memory and whatnot. Okay. So, for example, if we want to copy the data out of a parallel loop region, we use the copy out clause with a name of a variable and a region. Think of this as a pointer, right? And think of this as an offset from the pointer and this as the end of that region. So we are just trying to specify a region of memory that we want to copy over to the device before I begin the computation, or if we want to copy out of the device after I finish the computation. So in this case, you are saying that I'm going to create a pragma AC region that is going to be a parallel loop because I will be using the -TA equal Tesla. I know this is going to be executed in the GPU, right? And look at this computation here. Do I ever need to know what the value of A of I was before the beginning of the parallel loop region? I do not, because what I'm doing is I'm oversubscribing and rewriting the values of A without having to read the values of A. That means that I do not want to copy the data into the device, but I only want to copy the data out of the device. So in that case, what I can do is I can use a copy out clause to bring the data out of the device. So just to bring it in here, I'm just gonna do it like this because I tried to write on the other system, but I cannot. Oh my God. Here, there you go. So I have an array here in the host that we call A, right? That array is going to have some values, random, because they come from memory. And then I need to start some computation here in the GPU, but that array I do not need to copy these values over here. So what I do is I just allocate a memory region on the GPU here. That memory region may or may not have the same values, right? It can be any values. But then through the computation, I assign 0 to each of those elements in the GPU. And at the end of the computation, I take these elements and copy out the values into the CPU. If I have a structured data, meaning that if I only have that operation there and I have never referenced that memory region before or after the computation, then this memory region that is allocated in the GPU is going to be deleted and I will only be left with the CPU version, right? Let me see if I have any questions. Okay, no questions. So there you go. So in Fortran, it's going to be about the same, right? But in Fortran, as I said earlier, the range, the range script, like the syntax here, is going to be similar to the Fortran syntax, which is from the value 1 to the value n. So it's different because in C++ is from the value 0. If I say here 10, for example, it's going to be from 10 to 10 plus n, right? So it's going to be the beginning of plus the size. But if I am in Fortran, I'm going to do the beginning of and the end of. I believe, I think I'm like 90% convinced that that is the case. I'll have to go back and revisit my Fortran. Okay. So in data management, when we do data management, one thing that we probably want to do is to understand that we, as I was saying earlier, we allocate a value of A in the GPU, we copy that value of A from the CPU to the GPU, we execute the kernel, we copy the data out of the GPU, and then we deallocate A from the GPU, right? Look at this. Just by saying, I'm going to have a GPU kernel, and just by saying, please copy the value in and out of the GPU kernel, I am doing all these 5 operations of data movement and computation, okay? So just to be clear, the CPU memory is in blue, the GPU memory is in red, in orange, and they are different to each other. In managed memory, they do not look different. They look as if they were exactly the same. Even if the runtime decides to make copies and data movements and whatever the runtime decides to do, they will just be looking as if they were different. But in non-managed memory, meaning like basic data management, this will be completely different to each other and the pointers will be completely different to each other. Okay, what operations do we have for this? We have copy, which is copy in and copy out. So I'm gonna explain copy in. Copy in is take data from the CPU into the GPU. Copy out is take data from the GPU into the CPU or the host. Host to device, device to host. And then this one is host to device and device to host. And there is a fourth option that is create. And create is going to be, do not copy any data. I just need to guarantee that I have a working memory space that is allocated so I don't segfault, right? So that is just to say, I don't care about the values that I have on the host or the device. I just need the memory to do something. And this is really useful whenever you have temporary arrays that you need to have in the device, but the result of those temporary arrays are not important for the final result. Okay. Array shaping, there you go. Yeah, I was right. So the way that we specify, one thing that you have to consider, and I don't know how familiar you guys are with pointers, but remember that whenever we have a pointer, what we have is a memory, is the value of a memory address in like a location in memory, right? And what originally, what OpenACC and all these programming models intended to do was to always copy data that was contiguous to each other, meaning that from a specific pointer, you were supposed to be copying data that was from that location until from that location to a size of that location, and it was going to copy all that region of memory, right? That has changed. Like, for example, OpenMP introduces declare mappers, which is something really complex to try to make fancy memory allocations on the GPU. But in the basic one and the ones that we are concerned about here, we are going to be seeing this as a pointer of memory, right? Like as the location of the memory where the data is in the host or the device. Then what is the beginning? What is the offset from that memory location to the beginning of the data that we are interested in? And then how long is going to be my data from that beginning of data? So just so I can draw it, I have a memory region here. The beginning location here, it's referred to as, in this case, array, right? Like it's a pointer to that beginning location here. I'm gonna do it like this. So it looks like a pointer, right? With an arrow. Actually, looks like a pointer there, right? So I have a pointer to that beginning location, but then I can set up a length, sorry, a beginning offset. Let's say that I want to copy this region that I will highlight in purple, right? So I specify this location here and I specify this location here. This location will be the starting index and this location will be the length of this purple region. But in Fortran, it will be the starting index and the end index, right? So let's say that I want to copy, this is of size 20, right? So this of size 20. And this one here is supposed to be 5. And this index here is supposed to be 10, right? So I'm copying 5 elements, right? So in Fortran, I will say array 5 colon 10, but in C, I will say array 5 colon 5. I will move that in a second. Because in C, they care about the distance in between this point and this point, and in Fortran, they care about the beginning index and the end index. Okay. Okay. That's important. Now we go into profiling GPU code. Now, when we profile GPU code with data movement, if we want to use managed memory, right? First, we have to guarantee that the device supports managed memory. And I discussed this briefly before. If I go into my Jupyter notebook and I look at any of these files, the first instruction that we have here is give me the information of my accelerator. If I run that, I will get all the different information, and one of them is, do I support managed memory? Managed memory was introduced like a long time ago, so I assume that most of the devices that we have nowadays are going to support managed memory. Then we also have a device name. Yeah, there is a possibility of compiling or building multiple devices, right? And we also have an amount of memory that we can use in the GPU. So that means that we cannot exceed, if we use, for example, a create clause, like we were discussing earlier, we cannot exceed that memory, okay? Then, how long do I have? It's because it's too many. How long do I have? 7 until 3? Or Carlos?
3:30. Oh,
3:30,
sorry.
okay.
No, 3. Until 3.
3,
Yes.
okay.
Yes,
Perfect.
Yes. The other one.
So let's move forward. And okay. So here, whenever we do regular, okay, so whenever we have a region of code where we have pointers, immediately you can think of it as, I do not know what the size of that memory region is. But if we do not have pointers, but we have a stack arrays, the compiler has, within the context of the compilation, information about the size of that particular pointer. So whenever they do, they will be able to generate default behaviors, and you will be seeing that if you use minfoaxl, you will be seeing that in the compilation, okay? If you go into a profiling, now you will start seeing some of the regions of memory that are going to be memory movements from and to the device. And this is one of the big parts of GPU programming. You have to always be aware of where your memory is and try to avoid as much as possible moving data from the host to the device. There are cases where you cannot avoid it. Yes, the bandwidth in between the host and the device has been improving considerably, but any data movement in between host and device is tend to be considered costly and it's better to be avoided. That doesn't mean that you always have to, but that's just the like a rule of thumb that used to work, that tends to work really, really good. Now, because under OpenACC you have CUDA, that means that the calls that you're going to be seeing in OpenACC when you profile it are going to be really similar to the ones that you will be writing if you were to be writing CUDA code. So in this case, we will start seeing memory copies from the host to the device and memory copies from the device to the host, and they will be separated in the profile. Now, one thing here is that most likely whenever we start to work on a code with data management, sorry, not with data management, with data movements, quickly you will realize that your performance is going to be worse. And that is because the first intuition that we have is that we generate a kernel or a parallel region, and immediately we put the data movement in there. But if you consider in our case, we have a while loop, right? And that while loop has two different functions. One is called swap, and the other one is called calc next, or calculate the next one. Now, if you were to use data movement in each single kernel region, then it's better if I show it here. What is it here? I'm in the Fortran version. So we have this while loop here, right? And then we call calc next, and then we call swap. If we go and take a look at calc next and swap, imagine that I have a Pragma ACC kernel here, right? And I do the copy of A with the appropriate size and of a new with the appropriate size, right? So now I begin in the while loop. I go into this function and I copy the data over to the device. I make the calculation and I copy the data back to the host. Then I go back here into the while loop. I go into the swap and I copy the data over into the device, do the swap of memory, and then I copy the data back into the device. Question, do I need the data going from the calc next to the swap? Do I need the data on the host? Exactly. We do not really need the data in the host, right? So it means that if you just think of the data movement as something that happens in the kernel and you attach the kernel to a data movement, most likely you will have terrible performance because you are adding extra data movements that are just not going to, that are going to hide away the improvements that you get in computation. So this is just to say, do not get scared if the first time that you do data movement is the performance is crap, okay? But if you go and profile the code, you will immediately see that the problem in your code is going to be the data movements, right? So what we can do first is we can try manage memory. That means we do not worry about the data movements. We leave the program, we leave the runtime to that decision of moving data back and forth. Or we do not do manage memory, but we do unstructured data copies, or we use the data directive, which is our next step. Okay, I will give you guys 10 minutes to play with the module 4. I know it's too little, but I don't want you guys to miss out on the module 5 before I finish. So 5-10 minutes to play. Yes. By the way, I didn't understand how it works for multidimensional arrays. OpenACC is able to detect the second and third dimensions of your arrays. Yes. I'm trying to remember. The original rule in OpenACC is that the data movements that you were trying to do, you were supposed to do them in contiguously, but that has changed recently, and I'm not 100% sure if OpenACC supports these contiguous arrays. Like, let me just go back to example before I do this. All right, so the first thing that you have to understand is that multidimensional arrays are often seen in C as a single pointer, right? Like when you have a 2D array, there are two ways that you can do 2D arrays. The first one is you allocate a really large memory region, and then you manually do the offset to the different dimensions, like what we do here with the offset here, right? So whenever we calculate the offset, we take the rows, we multiply it for we take the number of columns, we multiply it for the row that we are trying to fetch, and then we take the column and we add it to the element, right? So we do the offset by hand. So from the perspective of OpenACC, this is a single dimension array. If you were to have a multi-dimension array inside of this function, like if you were to create something like that, then yes, you can use multi-dimensions here, right? As a rule of thumb, it's better if they are contiguous, but I believe that recently they have changed it so they do not have to be contiguous, and I will have to check with that, check that offline, and I will get back to you on that. But if we were to like, let's say, to move these regions, I can always say 0n and 0n, and that should work, right? For Fortran, the story is different because Fortran supports multidimensional arrays out of the box, right? So in Fortran, if I pass a multidimensional array as a parameter of a function, I can just use that inside because I already have information about the size. That's one of the advantages in Fortran, is that because the arrays are a basic data type of Fortran, then the support for dealing with arrays is a little bit more intuitive for Fortran programmers. Do you agree, Luis? Absolutely. Okay. Okay, we'll go get some water and we will be back to continue this. Okay.
On the website gci.com, they say Windows instructions.
Hey, Google,
Hold down.
stop. And I said, okay, and then Google thought that I was talking to them. So let's take a look at the result. Let's take a look at the solution they provide here with the module 4. English, C, solutions. So the basic data, right? This is where we said that we just put the Pragma ACC parallel loop here, and we copy the data back and forth from the host to the device. Look that you can do computation here, like because we have a 2-dimension M and N, but we know that this is a single dimensional pointer, then you can just do M and N. When you have the other way, I forgot to mention this, the other way that you can do multi-dimensional arrays is by allocating pointers and then allocating memory into those pointers. And when you have that, you cannot just use this copy out of the box unless you are just working on a single region of memory, because the compiler, it's usually the case that it's really hard for them to understand the pointers to pointers. So what you do is you use unstructured data movement, which is something that we'll see in a second, to solve that issue. So here we do the copy, we do the loop, right? Then we do the copy, we do the loop. So because of this, as I was saying earlier, this version is going to have a terrible performance in comparison to the sequential version. Okay, questions? Let's go to module 5. Okay, so now that we have talked about the basics ones, right? Like we just want to create a kernel, do the data movement, and come back. Then that's just what we do. We just say copy in, copy out, copy, or allocate, and that's it, right? But we want to have more control than that. We want to be able to say, I want to move the data, but I don't want to have computation associated to that data. I don't want to always be stuck with a beginning and end region, or a bracket, beginning bracket and an end bracket, right? So the way that we can do this is by doing explicit memory management, where we're going to specify where exactly in the code we're going to do the data back, move the data back and forth from the host to the device. Okay, so this is always going to be the case that it's really weird that you have a case where you just use the data basic movements, because if you think about big software project, you're going to have classes, you're going to have multiple compilation units, you're going to have different structures, and you want to be able to manage when and where do you move the data around. And with all that complexity, if you take into account all that complexity, then having to create a kernel, like, I don't know, like I go and create a huge parallel region at the beginning of my main program and then all the way at the end, and then I have to deal with dynamic kernels or like all these crazy things, it's just not going to work out, right? So you need to be able to control, to have the ability to define places in the code that you want to move data back and forth. So there are two ways that we can do this, okay? The first one is the data directive. So now instead of saying parallel or kernel, we are gonna say data. So we say Pragma ACC data, or we say ACC data clause, and the clauses that we want to have, okay? And when we do this, what we are saying is, whenever the code reaches this bracket, I'm going to do the data movement, but I will not have any computation whatsoever. And at the end of the bracket, I'm going to have a data movement, and I'm not going to have computation whatsoever. Look, that I still have a region, right? But I will be able to say, I do the data movement and I worry about the kernel somewhere inside, even if that inside is going to be a different function. So in this case, the ACC data, the important thing to consider is that whenever you see an ACC data, you will not create a GPU code. You will only create data movement that, like, you're only going to have calls to data movement runtime functions that will move the data back and forth in between the CPU and the GPU. But if I had, for example, I have an example later on. All right, so the different classes that we are going to be using here in these classes are exactly the same as that we had before: copy, copy in, copy out, create. Meaning I can even allocate data here in this point, and then later on use that data allocation in the other one. The array shaping works exactly the same as we had earlier, as we explained earlier. And this is the multidimensional arrays, right, that we also discussed by one of those questions. You can also do partial arrays, meaning that you can select just a few elements of the array. This is really useful when you do multi-GPU programming, because when you have multi-GPU programming, one thing you want to do is be able to chunk your data into all the GPU devices that you have. So you can say, I'm going to have 4 GPUs, so I do something like this, n over 4 times I for the data movement, and I just give a different region of memory to each of the GPUs, and they work on that region of memory independently. Okay. In this case, we have the pragma-ICC parallel loop that we have before, but we have to create a pragma-ICC data, a copy in and a copy out. At this point of the code, this is host code. So this is CPU code, right? Only when I reach this point here is when I jump into a GPU code, okay? So the important aspect here is that I'm decoupling the data movement from the computation itself. Okay. I'm going to skip this just because of the animations are not working. And I'm going to talk about implied data regions. So there are cases where we do not discuss what memory we are going to be copying. And there are going to be default behaviors that are just going to happen because the compiler understands the memory regions that you are trying to copy. So in this case, I am explicitly saying that I'm copying the values, right? But if I didn't have this line here, it means that the compiler will try to see if it recognizes the size of A, and if it does, it will do the memory copy in and out of the region. This will happen as long as that memory region has not been copied over into the device. So if the pointer A is recognized as a pointer that has already been copied to the device, then it will not try to do the data copy, okay? Another important aspect is that we will have a lot of integer, like a lot of scalar values. Like let's say that I have an int b here equal to 100, right? So if I do this, there is an implicit behavior for the scalar values that is usually first private, that will take the values from the host into the device and copy the value, the original value that I have in the host, right? So I do not have to specify it here, but if it sees and knows what the value is, and if it is a scalar value, it will just do the copy and it will privatize the value into the GPU. We'll talk about that later on a little bit more. Okay, so in this case, I do explicit. In this case, I do implicit. I will call this implicit more like that, but let's give them that. Okay, so this here may or may not be present, and this still will be implicit if the compiler knows the size of A, right? If the compiler knows that we are trying to access 100 elements of A, and it knows the shape of A, then it will be able to do the data copy. Okay. The other thing here is that because I have an implicit memory copy here, because I already had a copy here, that means that the compiler recognizes that A has already been mapped when it reaches this point. So even though that there is an implicit memory copy here, it will not do it because it knows that the data of A is already present in the device. Okay. This is more or less what we were talking about. Okay. So that is when I have a region of code, when I say, okay, I'm going to create a region of code that I'm going to say the beginning is going to be my data movements to the device, the end is going to be my data movements to the host, right? But sometimes I just want to have a data movement. I don't want to think, am I at the beginning or am I at the end? Or I don't want to always be able to have like a bracket at the beginning and a bracket at the end. I don't want to have code that is completely enclosed. I want to have the ability to just go into a random function in the middle of a class and say, please copy the data of this particular data member of my class into the GPU. And so there is unstructured data directives that what they do is they allow us to just say, at this point, do the data movement. If it is an ACC enter data, then I'm moving data to the device. And if it is an ACC exit data, then I'm moving data from the host, from the device into the host, right? That means that it doesn't make sense for me to have a copy out in an enter data, and it doesn't make sense for me to have a copy in an exit data, because there is already a direction in there, right? So you can say copy in an enter data, and you can say copy out in an exit data, or you can say allocate in an enter data, and you can say deallocate in an exit data. And this here does not have to be in this order. You can have this in one place and then this yet in another place of your code. They don't have to be one next to the other. It is a good practice to have, if you ever create an enter data, you should have an exit data somewhere in your code, in your destructors or in the end before the return 0 of the main function somewhere. You do want to make sure that you deallocate the data from the device, right? Or copy the data or do something with it. Okay, so in the exit data, you do the allocation, and the way that you do it is with the delete clause, right? So in this case, for the enter data, you will have copy in. For the exit data, you will have copy out. And for the enter data, you will have create. And for the exit data, you will have delete. Okay, so in a basic example, we have the same thing. We create an enter data here. Look that I do not have brackets anymore. I could have this somewhere else. I could have this in another function, and this in another function, and this in another function. And as long as this is the control flow of operations that I execute, then I will have a data of A, B, and C copied over to the device. The computation here, it will recognize that values are already present in the device, or we will tell the compiler that the values are already present in the device. And here it will just exit the values from the device, okay? So I'm going to skip this because of the, oh, here. Look that I am creating a value of C here, and I'm copying out the value of C here, right? I do not need the value of C to be moved from the host, so I create. And I do not need the value of A and B to be moved from the device. So in theory, I should have a delete here, which they do add it here, delete A and B, right? So the differences are clear. The structured data movement can only be in a single function. It has to have, like, they already have an implicit beginning and end, right? You do not have to have a pragma ACC at the end, so it's a little bit easier to look at it. But that means that you cannot just split this into multiple functions, right? And the other important aspect is that you know where the data begins, like where the data exists in the device, and you know when the data dies in the device. But in the unstructured data movement, you have to think of allocation and deallocation as two independent operations. You can have this anywhere in your code in another function or in another compilation unit, and you can have this anywhere in your code in another function or in another compilation unit. So this one has a lot of flexibility. This one looks cleaner, but this one does not always work. So you always have the possibility of doing it like this. Have 15 minutes. For example, here, we have a function here that does the allocation. We have a function here that does the deallocation, and we have the main program that has the kernel. I do the allocation and I do the deallocation here. Now, in this case, we have everything in a single source code. But what happens if we have this in a single library on one end and we have this in a second library on another end? Then whenever the program tries to compile this, it may have sometimes issues understanding if the pointer of A, which is the pointer that is allocated in the device, right? This pointer here that is returned here, is or is not in the device. So there are going to be clauses that allows us to specify what data is already in the device, so the compiler doesn't have to deal with that problem. And that's what we do in here. Okay, no, in the next one, this is data synchronization. So far, so good. I have a question. is it advisable to use the unstructured approach from a software engineer perspective? Seems really hard to debug. If you consider it from purely OpenACC, I agree with you that it looks cleaner if you have a structured data movements. But there is a caveat here. Whenever you try to make code in, for example, classes, it is a really nice approach to have an enter data in the constructor and an exit data in the destructor. So whenever you create an object, you immediately have that object being mapped into GPU, and you can have methods that work on the GPU and access the data already present in the GPU. So there is this flexibility that will probably place nicely with other software engineering techniques, right? That will help you when you have enter data and exit data. How do you manage the lexical scope of the array variables when the unstructured data movement is called from a different functions? So you got to understand that the enter data and exit data in runtime work from the perspective of pointers and not from the perspective of values. Because once you compile a C code, there is no such thing as A, B, or C, or pointer, or whatever, right? Like the C code, when it is a binary, it does not understand, because the computer does not understand the syntax where the information comes from. So the runtime system relies on pointers, on the values that you are using to point to that particular location. So in this case, pointer, which is the name of this function here, is not important for this name that is A, as long as the value that you get in A, the 0xFF534, whatever, is the same that you're gonna get in the pointer here, right? Does that make sense, Aurelio? There is a way you can deal with this, and it is, you have a table in your head, and you count references to that particular memory location. And you always think of the table columns will be the host device, the host pointer, the device pointer, and the number of references. The number of references are the number of functions, right, of data directives that are affecting the implicitly or explicitly affecting that particular memory location. So if I consider this in my table, I have this memory location that is returned by the malloc in the host pointer. I have the resulting host device pointer from the center data, right? So I know those two are mapped, and the reference count is going to be 1. When I reach this point, because I have an implicit data movement here, my reference pointer is going to increase, my reference count is going to increase to 2. When I leave this region here, it goes back to 1. And when I reach the delete, that reference counter goes to 0. So you always think of this table because it allows you to think of my device pointer, my host pointer, and how many times have I referenced the device pointer in the device. Is that useful? Awesome. Okay. Update directive. If we have an unstructured data movement, that also means that we have, sometimes we want to be able to move the data at any moment, right? Like I allocate some memory, and then at some point I need to synchronize the values in the host and the device. Remember, you always have to have this figure in your head. You have some memory in here, and you have some memory in here. They do not need to be in synchronization. They do not need to have the same values. If you're in managed memory, sure, you have synchronized values. But if you're not in managed memory, then you have to have some sort of possibility to do the synchronization in between the two. So what you do is you use the update, right, to be able to specify if the host wants to update the self information, meaning that it wants to get the information from the device into the host, right? If you, in other ways, if the host data agrees with the device data, right? Or in the device, if the device data agrees with the host data, meaning that in this case, you are sending the data from the device into the host, and in this case, you are sending the data from the host to the device. I really don't like the self and device names, but that is just me. So what you are doing here is you are ignoring that reference table that you were discussing, and you are just saying, at this point, I want you to copy the data to that particular location. And of course, that means that the data has to already be mapped into that region of code, because otherwise is an operation that is invalid because you do not have an allocation of memory in the device. So this is going to be from the CPU memory, you do update device into the GPU, and from the GPU memory, you do update self into the CPU. Okay, so you can allocate, going back to the same result, you can do allocation, deallocation, right? And you can do initialization, and then after you do the initialization, you do the update, right? So it means that you can do your mallocs independently on one part of your code, then you can do your data movements independently with the update class, and you can do your freeze in another part of your code where you remove the data from the device, right? And I don't know if you remember earlier, I mentioned that most likely you will not be able to modify the initialization task, but sometimes you do, especially when you have to update the information in the device. It's not for performance, it is for correctness. Any questions up to this point? Okay. Data structures and classes. I don't know how many of you know, but when you create a data structure in memory, and that data structure is based on types that are known in terms of the size of the type, that the compiler tries to allocate memory contiguous to each other. It tries to put, to allocate, in this case, a region of memory that is size 3 floats, where it puts the float, the X into the first element, the Y into the second element, and the Z into the third element, right? So they are contiguous to each other. From time to time, there is something called padding, that is adding or attaching regions of memory that are not contiguous just for the sake of aligning the memory accesses, right? If, for example, I have a weird data type here that contains 3 bytes, three bytes, right? I will have a padding of 1 byte here, just so I have an aligned memory access to Y. Okay, this is a little bit of memory management in the compilers and all that, right? That means that because this is a contiguous memory region, whenever we try to allocate or to move as data structures into the device, if the size of that data structure is known, it is possible for the device to be able to handle that. Whenever I do not have a memory region that is known, what I will have to do is I will have to map independently the array, right? Let's say, for example, I copy V, so I copy these elements, but then immediately after that, I have to go and create the array of V.array because of what we were mentioning earlier. Let me draw this here. I have my structure here, and inside of my structure, I have a pointer that is called array. Oh my God. I have that pointer that is called array, and then I have a second memory region here. So that pointer works like that. Okay, so this is my pointer to the array. The first data movement is going to copy the array, the pointer, and the value of n here, right? So this is my array, and this is my value of n. The second one, it will dereference that pointer. It will follow this purple line here, and it will copy the values that are pointed by that pointer. So whenever you access that pointer in the device, the data region is present. Is this clear, or is this too complicated? I think one really important element here to consider is, I don't know if you are familiar with pointers, but every time that you see a pointer, think of an integer which value represents a memory location, or it's usually the size of the word, so it will be 64 bits in most of the current computers, which value represents a memory location, right? So if I try to print this particular pointer here, what I will get is the memory location of this memory region here. That means that if I want to move this memory location, I can use that information to first map this, and then second, map this region of memory that is pointed by the value array. Okay, I don't see any questions, so I'm just going to assume that is fine. Then there is classes where sometimes you may be able to copy a class because classes have similar data structures or memory allocation structures in the device. Once you start going into virtual classes, this becomes really complicated and it doesn't work that well. Okay, so just so you know, you can work with classes. It is possible. When you do inheritance and you do virtual, pure, like you do interfaces, then it becomes really complicated to manage. Okay, so this is a really well-known scheme, like software engineering scheme, that will just have a method that will update the information in the device and have a method that will update the information in the host. So you can do something like this. Is new recognized memory allocation directive C++, or is it required to use malloc? Yes, it is recognized. Like you can do new and then take that pointer and use it for the data. You don't have to use malloc. Yeah, that is correct. Okay. I will skip because I only have 3 minutes. So I will skip this part and I will finish like this, just so we have a couple of minutes for questions. Okay, the other modules that we have here, you know where to find them. Module 6 talks a little bit more about loop optimizations, how to define different sizes of loops, right? So you can take a look at it later. It talks about data privatization. I think that's a really important aspect, but unfortunately, we will not have time to cover it. Module 7 talks about asynchronous programming. This is just really cool to do. And most of the really clever ways to do it is through doing asynchronous programming. Module 8 is interoperability, if I recall. Interoperability with CUDA, something that some people were interested in. Take a look at module 8 for sure. Okay, there is a political answer to that question. I'll respond it in a second. Module 4. Here you go. Interoperability. And then the last one is, I believe it is multi-GPU programming, and it may also be MPI programming, a little bit of MPI. So do take a look at these codes. Okay, so Esteban, what is the future of OpenACC with this new device like neural networks, neural processors, ARM processor family, FPGAs, and so on? Right now, if you take a look at the Department of Energy Labs, OpenMP has been taking a lot of, it's becoming stronger as an option for the programmers, but it does not mean that there are applications that are still using OpenACC. In fact, there is currently an effort from Oak Ridge called CLAC that is a programmer support for OpenACC in LLVM, using similar runtimes and the ones that OpenMP has for LLVM. So just kind of like creating a front end for OpenACC in LLVM. So I don't think that OpenACC will necessarily disappear. The other thing is a lot of these new architectures, for example, the neural processors, right? They tend to have libraries already in place that allows you to do the manipulation of the data. It's not like you have, it's not necessarily a general purpose computation. in the case of FPGAs, it is a general purpose computation. There is some investigations or some research done in the world of trying to use FPGAs with OpenACC. I believe there are papers out there, but it is still problematic to go from C and C++ into FPGAs doing that mapping. And so there is still an active research. In my opinion, I believe that we will have highly heterogeneous computers in the future, and that it will have to be a combination of what we have right now and a programming model that is a little bit more descriptive of the scheduling operations and the organization and orchestration of the program with respect to the computation and where those computations happen to be executed. So I don't want to end with just saying, I don't think that this will be useful in the future. I think that these programming models will be changing a lot in the future, but it doesn't mean that whatever you do right now, and if you want to use GPUs right now, is really useful because of the inertia that these programming models have, OpenACC and OpenMP in particular. Then it is likely that future architectures are going to be supporting them, and it is likely that somebody will have to write some sort of translation to whatever future comes in front of us. Because as application developers, you cannot just wait for them to you cannot just wait for those elements to come. You have to use whatever is available to you right now. So right now, some advantages that OpenACC has over OpenMP is that it is still really clean in comparison to OpenMP. OpenMP, just the specification of 5.0 was 666 pages. 5.1 was a little bit more than that, right? So it's a really big specifications that is really hard to support, and it's really hard for developers to keep up with all the different details of that specification. OpenACC is much smaller than that, and even though that it has increased in size, it has a similar objective where they try not to expose too many of the operations to the programmer. OpenMP, on the other hand, is currently being supported by many vendors, and there is, for example, if you take a look at the efforts that Cray are trying to do, they are focusing on OpenMP. IBM has support for OpenMP offloading. Intel is providing support for OpenMP. So many of the compilers that are coming out right now are coming out with support for OpenMP. But that is also true because they are basing off LLVM. And I think that paying attention to what LLVM is and what LLVM does right now is important for the future. I hope that answers the question, Susan. Okay, any other questions? I think it's already 3:03, so I don't want to take over the other speakers' time. Oh, okay, so we have 30 more minutes. You're welcome, Alberto. Glad you like it. I'm going to leave my email. I didn't do that. I usually do it. I forgot here. If you have any questions or comments or concerns, or you want to say whatever you want to say, that you can reach me in that email. Okay.
Oh, Jose, he had is more. Is not technical question, of course. It's about the TSAB and about the integration of a strong community around the high performance computing in Colombia. What is the real requirement for one person that probably are running in a BS or probably in the postgraduate and like go to the national lab? This okay, so what is your advice for that?
So a couple of years ago, we were looking into support from Outreach to create this. Thank you very much. To create, you're welcome, Luis. To create these sort of events, right? Like workshops and training materials and all this. And one response that we got from Outreach was, look, we do not have users of our systems in Latin America, not because we do not allow them to do it, it's because we do not have the people applying to the resources, the computational resources. A lot of the DOE, Department of Energy labs, like Argonne, like Oak Ridge, and others, they use the idea of open science, meaning that as long as your science is open and publishable, they will allow you to use the resources for free. But that comes with the fact that you have to justify those resources. There are many ways that you can do it. One is applying to a special allocation. So there are processes in each of the lab and you'll have to look those up. And there are also ways that you can talk to people within the national labs to ask for a discretionary director's discretion is called, and it is an allocation that the directors of the different programs in the lab are able to allocate for specific programs that do not necessarily mean that they have to be big. However, whenever you want to reach those national laboratories, you already have to have some code written that you can go and justify them and say, look, I have already wrote this code, it's running on this device, I'm reaching this limit, and this is the limit that I want to reach, and so I need this many resources for doing that, right? So it is possible to do it. Now, my recommendation is, if you want to know more a little bit about this, if you want to know a little bit more about this, go into the HPC Americas Slack channel that we discussed at some point during this week and talk to people there, because we have people like Veronica who are really supportive of these efforts that will guide you on what you need to do in order for you to get those resources. I am considerably new to Argonne, so I have to still figure out how to make that happen. But if you have a specific problem and you say, hey, I want to use the resources, I can always reach out to people within Argonne to figure out how to make that happen. And it is possible to make that happen.
Thank you, Jose. And another question is more, what is your advice for this community? 20 people that say long week, training, quantum, HPC, etc. No, what is the next step? What is your advice for this community?
So this field, HPC, has a really nice international community, and it has an idea where HPC centers, they usually need science to use their systems, right? It's really important for those systems to be able to be able to have numbers that say we enable science, right? The economical bar for starting HPC may look really high with respect to acquiring the equipment, but in reality, it can be really low with respect to the amount of available resources that exist, right? So my advice right now is, do you take a look at the resources that you have locally, use those to be able to port your codes, create new projects, share those projects. Always, always, always have a repo and an infrastructure that makes the projects open. If you have a project that cures cancer, but it's someone in your computer, that is useless for the HPC community because nobody else is going to be able to use it at all, right? So do open your projects. Now, once you have something working, start reaching out to the community, because the community always wants to provide feedback. So for example, you're working on OpenMP and your OpenMP code is not working, it's breaking the compiler or doing something. It is really easy to reach out to the LLVM community and say, hey, I have a bug in this compiler, please help me fix it. And people will jump into fixing the problem, right? Like there are people that are paid to fix the problems that you have in the compilers. Once you have code that is running on your system or that is running on your local clusters, reach out to communities to be able to obtain larger resources, right? To be able to scale the problem, right? And always try to attend all the different, try to connect, because the HPC community is driven by those connections. It's driven by the resources, of course, but it's also driven by those connections. It's really, really important to connect to people and to do networking in this community. So I think the most important advice for you guys is, do not think this is something impossible to do. It's just that it looks that way because the computers are crazy expensive and they are infrastructures that we do not think that we have available right now, but we do, and try to do whatever it takes to begin to start your projects, and then after that, reach out to people so they can help you get the resources you need. And open source things, right? Like everything, open source everything.
Perfect.
Other things that you can do is you can join community, like you can start working on LLVM. LLVM, there is always a shortage of people that know about programming compilers, and there is a lot of money there. If you know LLVM, how to hack into LLVM, and you provide, like, people start seeing that you are always attending the LLVM meetings, that you are pushing into a pull request and things like that, I'm pretty sure somebody will reach out to you and say, hey, we need you, because compilers are complicated and they are really needed into a lot of infrastructure.
My last question, Jose, is what is your advice for this community and how to ground this community? Yeah, because we started 4 years ago, now running our 4th HPC Summer School, and now what is the next step? How Rafael, Pablo, Martin, Leandro, Lauren, etc. can support this effort?
I think, for once, I think that the community has grown in seriousness. Like when we started this 4 years ago, we didn't have a website, we didn't have an image, we didn't have a name. And right now, it does look like we are someone in that we are going to start being recognized by the work we do. I believe that we need to start thinking more in terms of academic programs, right? Like, what if we start thinking of an HPC conference and we start thinking of the possibility of having an indexed workshop or something like that? And also probably be regular in and a little bit more open in who joins the community. Like the meetings that you usually guys hold on Thursday mornings should be something that is open to the community, and that should be anybody who wants to join is welcome to join, or have a space for doing that. And also have a clear schedule of the different talks that we are going to have across the year. I think those are the 3 main elements I believe that are important right now.
Okay, Jose, thank you very much for your attention and for trying to support our effort too. I believe that this time for open the mic for question, specific or more general question, probably.
Yeah, feel free to discuss any topic, to talk about your experience, to whatever you want to say. Tell us about your breakups.
Hi, I also was wondering, is it this tool OpenACC like feasible to use like in exchange of MPI? Because I saw you say that you can use multi-GPUs, can also use multi-systems, or that is only like for GPUs?
Okay, OpenACC can support multi-GPUs when the multi-GPUs are in the same device. When you want to use multi-nodes, then you still need to go to MPI. But there is within the material, there is information about how you can create MPI, like data movements and things like that, and then use OpenACC within MPI. OpenMP is the same right now, but I know of people that have been working in multi-node OpenMP, which is more or less supported by LLVM, but not necessarily in a good shape right now. So I believe that this is something doable because you already have explicit data movements, you already have explicit recognition of computational regions that you can move back and forth, but that is something that is still not there. So just keep paying attention to what is coming up. And for now, just consider using it in a single node.
Right, thank you. Also, I have a question for the organizers. until when are we going to have access to the HPC to test the codes here? Because they are already set up and easy to use.
Carlos,
Yep, I'm here.
do you know until when they can use the U Rosario the Jupyter Hub?
Jupyter Hub.
Yeah.
Let me check. Let me check. I will ask.
I'm pretty sure you can use it today. Like, I don't think
Yeah,
that will
for
delete
sure.
anything. Yeah.
No, no problem. Today you can, but let me just check. That's a good question. Let me
Right. So-
double check and I'll answer it. Yeah, thank you.
Mhm.
Right, thank you.
It may be good if we can do it, and if we can use it until next week, until Monday, so they have some time in the weekend to play with it.
Yeah, sure.
At least until Monday.
Yeah, I think that should be no problem. Yeah, okay. Meanwhile, I mean, you can, we will take a break. So we will be back at 15:30. So 13 minutes from now. So we'll take a break and I will have your answer after the break, for sure.
Thank you, Carlos.
Thank you, everyone. Have a great day.
Thank you. Thank you. Thank you also, Jose, for your talk. Really nice talk. Everyone's very happy, I see.